Good morning, dear students. Our next topic, that is in physical chemistry topic, you have to study solid state. Only half of the portion it is taken by me, and the rest of the topic it is by Lucky. Okay, that is I am having my portion still Bragg's equation. Okay, after that Lucky will be taking that. So you have studied the solid state, isn't it? Solid state in your plus 1 plus 2 classes. And also regarding the introduction part, what are the characteristics of solids? That is what you have to go through. Okay, characteristics of solids. Usually, as you know, these solids, they have got a definite shape, isn't it? They have got a definite shape. Then also they have got they are highly rigid. Solids are highly rigid. Then they have got high mechanical strength. High mechanical strength. Then they are incompressible. That means while we are applying pressure, it cannot be compressed, isn't it? So that is, they are incompressible. Then solids are usually closely packed, not loosely packed as in the case of liquids or the case of gases. They are closely packed, and also there are strong forces of attraction which are holding the atoms together in the case of solids. Okay, so these are some of the characteristics of solids. And also usually two types of solids are there. The first one, they are called as the crystalline solids. Okay, crystalline solids. And the second category, they are amorphous solids. Crystalline as well as amorphous. Crystalline, then amorphous. So these are the two categories of solids, crystalline and amorphous solids. And also crystalline solids, in which are those solids in which they have got a definite geometrical pattern. Crystalline solids are those having a definite geometrical pattern. That means their arrangement are in a systematic manner. They are arranged in a systematic manner, and they will be having a definite regular geometry also. So crystalline solids means they have got a definite geometric pattern, and also they are having a regular geometry. That means they will be having a particular size or shape. Okay. And in the case of amorphous solids, it is just the opposite of crystalline solids. That means they have no definite geometric pattern. Okay, no definite geometric pattern, and also usually does not have a regular geometry, or they will be having an irregular geometry. Irregular geometry. So these are the two types of solids, crystalline as well as amorphous solids. And also usually these amorphous solids, they are regarded as supercooled liquids. Supercooled liquids with high viscosity. They are regarded as supercooled liquids with high viscosity. And also you have to go through some of the examples. See, for a crystalline solid, for example, sodium chloride, it is an example for crystalline solid. Sodium chloride. Then again sulfur, then sugar. These are some of the examples for crystalline solids. See, in the case of sodium chloride, Na, then comes Cl, then comes Na, then comes Cl, again here Cl, then Na, then Cl, Na, like that it goes on. Okay, so this is in this structure it has got a definite regular geometry, isn't it? But in the case of amorphous solids, it does not have a definite regular geometry. And also example for an amorphous solid is for example, glass is an example for an amorphous solid. Okay, so amorphous solids means they does not have a definite regular geometry. And also some other amorphous solids are, glass is an example for an amorphous solid, then rubber, again an amorphous one, then plastic. So these are some of the examples. Then again another important point to be noted is that these crystalline as well as amorphous solids, regarding the properties, these crystalline solids, they are anisotropic. Okay, crystalline solids are anisotropic. while these amorphous solids they are isotropic. So next you have to go through these 2 points. What do you mean by anisotropy and what do you mean by isotropy? Okay, so crystalline solids are anisotropic while amorphous solids are anisotropic. So next is isotropy and anisotropy. First of all, we have to see what do you mean by isotropy. So isotropic substances means the properties will be the same in all directions. Properties will be the same in all directions. That means they will be having a uniform composition. That is, while we are going through any magnitude, the properties will be the same in all directions. That means the physical properties will be the same. Normally the physical properties like refractive index, then mechanical strength, then thermal conductivity, and electrical conductivity. These are some of the physical properties while considering the case of the solids. So while we are moving through a particular, suppose if it is a plastic or a solid, suppose we are going through in any direction, what happens is that the properties will be the same in all directions. Okay, if we are taking it in any direction, that is, it will be having a uniform composition. So the properties will be the same in all directions. Such substances, they are called as isotropic. Okay, so normally these amorphous substances, that is rubber, glass, plastic, etc., they are isotropic substances. That means while we are going through any part of the that particular substance, while we are dealing with any part of that particular substance, we can see that the properties will be the same. Okay, then the next one, that is the anisotropic substances. Okay, so isotropic means it will be exhibited by these amorphous substances. Okay, then in the case of anisotropic substances, then anisotropic. In the case of anisotropic substances means the magnitude will be differing. The magnitude of their physical properties will be varying. Magnitude of their physical properties will be varying in all directions, or it will be differing in different directions. Okay, will be varying in different directions, or the magnitude will be different in different directions. See, suppose this is an example. See, this is and also this anisotropy property, it will be exhibited by these crystals, isn't it? Exhibited by the crystals. And also suppose this is a crystal. See, it is represented by black dots. Then this one again. Then okay. See here, suppose this is a crystal. And also while we are going through while we are moving through this direction, see the property, it will be like this. Only this type of atom will be coming in this direction. Okay, and again if we are moving through this direction, see, it's a combination of these two dark dots as well as the bright dots, isn't it? This is a dark dot. Okay, so in this case, see, in this case it is having some white dots, and here it is having an alternate dark and white dots, isn't it? That means the properties will be varying in different directions along the crystals. See here, if while we are moving like this, see, all are black dots, isn't it? Again, if we are moving like this, alternate black and white dots. Okay, so likewise, in the case of crystals, they are exhibiting anisotropic nature. That means the magnitude or the physical properties will be differing in different directions. So this is anisotropic substances. It will be shown by the crystals. Okay, so crystalline substances will be anisotropic. Okay. Then the next one we can go through. One term is also there, that means double refraction. Double refraction. You have to study this isotropy as well as anisotropy. Okay. So in the case of double refraction, see when a ray of light, when it is entering into the crystal, see when suppose this is a crystal, and when a ray of light, when it is entering into the crystal, this ray of light, it will be split into two components. Okay, this ray of light will be splitting into two components, and also these two components will be traveling in a different path. Suppose this will be traveling in two different paths and also with a different velocity. Okay, so these are the two different paths, and these two paths will be having different velocity also. So when a ray of light, when it is entering into a crystal, what happens? The light will be it will be split up into two components, and also the two components will be having two different velocities and two different paths. Okay, so two different paths as well as two different velocity. Okay, so this phenomenon, it is called as the double refraction. Okay, so that also you have to study what do you mean by double refraction. And also in your textbook there is an explanation of isotropy and anisotropy is also given, that you can go through with the help of this picture. Okay, then the next one, you have to go through the characteristics of crystals, or the external features of crystals. External features of crystals, that means how a crystal we can represent by some notations or with the help of some features. Okay, and also the first one to be noted is that for the crystals will be having certain definite surfaces. Okay, and that surfaces we can call it as the faces. Okay, so mainly these crystals have got mainly we are going through 2-3 points. That is, the first one, it is having faces, then another term, it is form, then comes the third one is the edges that you have to go through, then the fourth one, it is the interfacial angle. Okay, interfacial angle. So these are some of the important features of a crystal while we are considering. Okay, then again corners are there. So the important features are, the first one, it is faces. Mainly we have to go through the faces, then edges, then interfacial angle, then corners. Okay, so these are some of the features of a crystal. Now you have to go through one by one. Okay, so here in solid state mainly we are dealing with the cubic crystals. Okay, we are dealing with the cubic crystals. So for your easiness, I am taking a solid cube. Okay, so this is a solid cube. So with this with the help of the solid cube, we can explain each of the properties, so that you will be clear about the different features of a crystal. So suppose consider this as a single crystal. Okay, and also this crystal, it is made up of so many atoms. You just have a look at this crystal. So this is a cubic crystal. This is just the form of a cubic crystal. Okay, you all know this is a Rubik's cube, no? So then the next one, first one, we have to go through the phases of a crystal. Phases of a crystal. See, while considering these phases, how many phases are there? See, this is a phase, isn't it? This yellow color is a phase, one phase. Then red is another phase. Then green is another phase, orange. Then blue. Then white. Okay, so in total, how many phases are there for this crystal? See, one, and to the opposite of this yellow, there is another one, that is white, isn't it? So two phases. Then next, here one phase is there, isn't it? So this part, that means this one, isn't it? So it is blue. So 2, 3. So 1, just the opposite of 1, it is 2. Then 3, this one. Then 4. Then 5, then 6, isn't it? So 6 phases are there for this crystal, isn't it? 1, opposite of 1, there will be 2. So 1, 2, then 3, 4, 5, 6. Okay, so in total, this cubic crystal, usually for a cubic crystal, it has got how many phases? 6 phases. Okay, 6 phases. Cubic crystal, it will be having 6 phases. Then see, phases you can define it as, it is the number of definite surfaces. It is the number of definite surfaces. That is what we call as a face. Okay, and sometimes there will be like faces as well as unlike faces for a crystal. Like faces as well as unlike faces. So this is regarding the face. So this is one face. Okay, this is another face. Then the next one, third one, 4, then 5, then here it is 6 white. Okay. So next feature of a crystal, that is the form of a crystal. See, form means it is the all the faces of a crystal, it will constitute a form of a crystal. Okay, so a simple cubic crystal or a simple crystal means, simple form of a crystal means it will be having like faces. Okay, a simple form of a crystal means it will be having like faces. And sometimes if two or more simple forms are there, it is called as a combination. Okay, combination form of a crystal. So a simple form will be there with like faces, and if two or more simple forms are there, it is called as a combination. Okay, then the next important one you have to go through is the edge of a crystal. Edge. See, edge means, see here, this is one of the face, isn't it? And this is another face, this red face as well as the yellow face. Okay, so by the intersection of these two faces, that means the red as well as the yellow face, we can see there will be an edge. So by the intersection of these two faces, an edge will be formed. Okay, so this is one edge. Then again, this red face as well as the green face, two faces, by the intersection of these two, here an edge. Again, by the intersection of red and white, here another edge. Red and blue, another edge. So these are the edges of a face. So in total, how many edges are there? How many edges will be there? See, 1, 2, 3, 4. Okay, so opposite this side, how many will be there? Just opposite it is the orange color. So again 1, 2, 3, 4. So in total 4 plus 4, 8 is there. Okay, then again here two faces are there. One green and again yellow. So one edge will be there. Okay, so likewise 4 plus 4, 8, it is already there. So 8 plus 9, then 10, 11, 12. Okay, so in total for a cubic crystal, how many edges are there? 12 edges are there for a cubic crystal. 12 edges for a cubic crystal. Once more I will tell you. So these edges are formed by the intersection of two faces. Edges are formed by the intersection of two faces. So here this is the first face, orange face, then this is the white face. So by the intersection, one edge. Okay, 1, 2, 3, 4, then 5, 6, 7, 8, then 9, 10, then 11, 12. Okay, so 4 above the cube and 4 below the cube, then 4 on the sides of the cube. Okay, so total how many edges will be there? 12 edges are there for a cubic crystal. 12 edges. Then how many faces for a cubic crystal? 6 faces for a cubic crystal. Okay, so this is the case of a cubic system. Okay, so 12 edges and 6 faces. Then the next one, that is the interfacial angle. Interfacial angle. Interfacial angle. See here, this interfacial angle means it is the angle between any two faces of a crystal. Angle between any two faces of a crystal. It is called as the interfacial angle. See, suppose this is the two face. See, 1, 2. Okay, so this is the two face. So at this point, one angle will be there. Okay, into the inner side of this part. Okay, that is one angle will be there. That is while we are moving this line upwards. See, this is and the third axis. So if we are drawing like this, what happens? One angle will be there to the innermost part. That is, this angle will be the interfacial angle. So the angle between any two faces of a crystal is called as the interfacial angle. And also there is a relation connecting these three, that is number of faces plus interfacial angle and the number of edges. A formula is there, that is the formula, it is F plus C is equal to E plus 2. The formula is F plus C is equal to E plus 2, where F it is called as the number of faces. Okay, F is the number of faces, C is the interfacial angle. C is the interfacial angle. Then E is the number of edges. So F is the number of faces, C is the interfacial angle, E is the number of edges. So this is the relation connecting these three. Hope you understood these terms: faces, then edges, then interfacial angle. Then the next is you have to go through the symmetry in crystal systems. So for a cubic crystal, how many faces? 6 faces, and edges 12 edges. Then the next is symmetry in crystal systems. Symmetry in crystal systems. So here, for this for studying the symmetry in crystal systems, you have to go through mainly 3 types of symmetry. That is, we can call it as the elements of symmetry. Elements of symmetry. So mainly the elements of symmetry, there are three elements of symmetry. That is, the first one, that is the plane of symmetry. Plane of symmetry. Then the second one, that is the axis of symmetry. Axis of symmetry. And the third one, that is the center of symmetry. So these are the 3 symmetry elements for describing a crystal system. For any crystal system, it can be a cubic one or an orthorhombic or a monoclinic system. For any system, you have to explain the symmetry elements in terms of these 3, that is the plane of symmetry, then the axis of symmetry, and the center of symmetry. Okay. So this elements of symmetry, we can define elements of symmetry. It can be defined as this elements of symmetry, it can be line or an axis. Okay. It can be a line or an axis, or it can be a plane, or it can be a point. Okay, this elements of symmetry means it can be a line or an axis, or it can be a plane, or it can be a point, with respect to which one or more symmetry operations can be carried out. So with respect to these 3, with respect to any one of these 3, we can do the symmetry operations. Symmetry operations you must have been studied in your group theory, isn't it? So many symmetry operations are there. That means there will be a rotation, or there will be an inversion of configuration, like that, isn't it? So we are doing all these symmetry operations in terms of with respect to this line or axis, or with respect to its plane, or with respect to a particular point. So these 3, they are called as the elements of symmetry. So we can define these elements of symmetry as a geometrical entity such as a line or an axis or a plane or a point, with respect to which we can carry out the symmetry operations. Okay. With respect to these, we can carry out the symmetry operations. So this is called as an elements of symmetry. Then you have to go through each one of these 3: plane of symmetry, then axis, then center of symmetry. Okay. So first one, that is the plane of symmetry. Plane of symmetry. So here plane of symmetry means, from the word itself, it is the symmetry element is the plane, isn't it? So it is an imaginary plane. It is an imaginary plane, and it should be passing through the center of the crystal. Okay, imaginary plane passing through the center of the crystal. Imaginary plane passing through the center of the crystal, and while this imaginary plane passes through the center of the crystal will be divided into two equal parts. Okay, I am splitting the definition it is divided into two equal parts. Okay, this plane will be cutting the crystal into two equal parts. And also, what about the equal parts? It will be an exact mirror image of the other. It will be an exact mirror image of the other. So this is the definition for a plane of symmetry. So what is a plane of symmetry? It is an imaginary plane passing through the center of the crystal, and it will be dividing the crystal into two equal parts, and also these two equal parts will be the exact mirror image of each other. Okay, so that is what is called as the plane of symmetry. And see, I will show you this diagram for the plane of symmetry. So for that you have to draw a cube. Okay, I am not good at drawing, so please excuse me. See, consider this as a cube. Okay, this is a cube. Okay, so this is the first face I am taking. Okay, this is the first face, and the center of this edge here, the center of this edge, it is here. Okay, and again the center of this edge, it is here almost. Then the center of this edge, it will be here. Okay, then I am joining all these four dots. Okay, like this, then this one here, so again here. Okay, so you have got a plane, isn't it? So this is one plane. So this is a plane. Okay, so can you see this plane? This plane, it will be cutting. See this plane. This plane, this will be cutting this particular cube into two equal halves, isn't it? And also you have seen the definition for the plane of symmetry. It is an imaginary plane. This is an imaginary plane, and it will be passing through the center of the crystal. See here, the center of the crystal, it is somewhere here, isn't it? So this imaginary plane, it will be passing through the center of the crystal, then dividing the crystal into two equal parts. It is two equal parts, isn't it? This is one part and this is the second part. And also one is the exact mirror image of the other. So this is the definition for a plane of symmetry. Hope you understand this plane of symmetry. Again, I will show you with the help of a cube. Okay, so see here, this is the cube. Suppose this is a cubic crystal. Then so suppose I am cutting this this cube into two equal halves, and the plane which cuts the cube, it is like this. That means like this it will be cutting. So suppose if we are cutting this cube at this plane, that means it will be cutting through this center of the crystal. Okay, cutting into two equal halves. We can say that this is the plane of symmetry by which the cube is having. Okay, so this will be the plane which is the plane of symmetry for this particular cube. Okay, so that is the definition for plane of symmetry. And then comes the axis or line of symmetry. Then the axis or line of symmetry. Hope you understood the plane of symmetry. Then the next one, that is the axis of symmetry. Then again, axis or line of symmetry means the first point to be noted is that it is an imaginary line. The previous one, it is an imaginary plane for plane of symmetry. So here this is an imaginary line or an imaginary axis which is passing through the center of the crystal. Which is passing through the center of the crystal. And also this while passing through the center of the crystal, it will be showing exactly the same appearance. The same appearance will be shown more than once in one complete revolution of 360 degree. In one complete revolution of 360 degree. Okay, so here Suppose I'm drawing this axis of symmetry. Again a cube. So this is a cube. So here this is the center of the crystal, isn't it? And also axis of symmetry means it is the line passing through the center of the crystal. This is the line passing through the center of the crystal, and through this line I am rotating this crystal 360 degree. Okay, along this line I am rotating this crystal 360 degree. So while rotating this crystal along 360 degree, it will be showing similar appearance more than once. Okay, if it is if we are having the similar appearance twice, if we are rotating the crystal, that is, suppose if we are rotating this crystal, this is the axis of symmetry, this is the axis or line of symmetry. So while rotating this crystal through this particular axis of symmetry, so you are getting similar appearance twice. See here it has got, the cube has got different color, so we can't say like that. See, suppose blue and green, they are the same. So suppose I am rotating along this axis. See, blue and green are the same. Okay, so while rotating again 2 times, we have got the same appearance. That means this cubic crystal, it is having a twofold symmetry. Okay, so if similar appearance we are obtaining twice, we can say that that particular crystal, it has got a twofold symmetry, and that axis we can call it as the dyad. Okay, dyad, that axis we can call it as dyad. Okay, are you clear? Okay, so this is the dyad. So while rotating through this axis of symmetry, if you are having the same appearance twice, that is blue and green, so blue and green are the same, so I had got the same appearance twice. That means it is having this particular cubic crystal, it has got a dyad, it has got the axis dyad or twofold symmetry. Okay, likewise, if the appearance, similar appearance we are obtaining it thrice, then we can call it as, it will be having a trifold symmetry, or similar appearance will be occurring thrice and it will be a triad. Okay, similar appearance will be occurring thrice, it is a triad axis. And if the similar appearance, it will be occurring 4 times, then we can call it as a tetrafold symmetry or a tetrad. Okay, so it can be, the axis of symmetry can be dyad, a triad or a tetrad. If similar appearance occurring twice, then it will be dyad. Similar appearance occurs thrice, it will be triad. If similar appearance occurs 4 times, it will be a tetrad. Okay, so that is regarding the axis of symmetry. Then comes the center of symmetry. Hope you understood these two, plane of symmetry as well as axis of symmetry. These are very important, and you have to understand the terms. Don't by heart these particular topics, otherwise it will be difficult for you. Okay, then the next one, that is the third element of symmetry, that is the center of symmetry. Center of symmetry. Center of symmetry. See, the center of symmetry, it is the point. The center of symmetry means it is a point. Center means it is a point. Okay, so it is a point at the center of the crystal. That is the first point to be noted. It is the point at the center of the crystal. And also, when a line is drawn through the center, when a line is drawn through the center, it will intersect the surface of the crystal. It will intersect the surface of the crystal, at equal distance on either side. At equal distance on either side. Okay, so this is the definition for center of symmetry. It is the point at the center of the crystal. See, suppose this is the crystal. center of the crystal, and the point, it will be at the center of the crystal, that is inside the crystal. This is the point inside the crystal at the center. And when a line is drawn through this point, or through this center or this particular point, it will intersect the surface of the crystal at equal distance on either side. See, suppose when a line is drawn from this plane, it will be, see, this is the center of this plane. Okay, so when a line is drawn from this plane, it will be having such a distance, and then the second plane, the opposite plane, it is this plane. Okay, this plane, this is the opposite one. So again the center. So see, suppose this line will be meeting this center at equal distances. Okay, so that is the center of symmetry, the point at the center of the crystal, and when a line is drawn through the center, it will be intersecting at the surfaces of the crystal at equal distances on either side. Okay, so this is the definition for center of symmetry. Okay, then the next one. So for explaining a particular system, crystal system, we have to say that the total number of planes of symmetry, then the total number of axes of symmetry, axes AX, okay, plural, axis of symmetry, and also the center of symmetry. So these three constitute the total symmetry element of a particular crystal system. Any crystal system, it can be a cubic or an orthorhombic or a monoclinic or any system. For defining any system, we have to note down all these: the plane, the axis, and also the center of symmetry of that particular crystal system. Okay. Then the next one, you have to go through the elements of symmetry of a cubic crystal system. Elements of symmetry of a cubic crystal system. See, for a cubic crystal system, there will be two planes of symmetry. So first element of symmetry, that is the plane of symmetry. Plane of symmetry. And also for a cubic crystal system, it will be having two types of plane of symmetry. That is the first one, that is the rectangular plane of symmetry. Rectangular plane of symmetry. And the second one, that is the diagonal plane of symmetry. Rectangular plane of symmetry and the diagonal plane of symmetry. Okay. Then here for a cubic crystal system, see, while considering the rectangular plane of symmetry, see, first one, rectangular plane of symmetry. See, plane of symmetry, it will be like this. So first you have to mark the plane of symmetry. Okay, joining all the centers. Okay, joining all the centers. So this is the plane of symmetry. So here this plane, it will be cutting the opposite faces of a particular crystal system, isn't it? So see, suppose this is one face and this is another face. So while cutting, we will be having one plane of symmetry. Okay, so this is one rectangular plane of symmetry. So similarly, how many planes are there? So here by counting the number of faces, see the number of faces for a cubic crystal system, how much? It will be 1, then opposite it will be 2, that is here it will be 2, then 3, 4, 5, 6. Okay, so number of faces will be 6 for a cubic crystal system. So total, how many planes will be there? This plane, it will be cutting two opposite faces, isn't it? So this is one plane. Likewise, here one plane will be there, like this. That is, at this portion, we can cut this cube, isn't it? This is one plane of symmetry. Then this is another plane of symmetry by cutting this portion. This plane, this is another plane of symmetry. Then the remaining one more is that. So here 1, 2. So total number of faces will be 6. So 1, then just opposite this one. Then this is another two opposite faces. Okay, so likewise we can cut through this. Then the third face, opposite faces, these two, isn't it? So 1, 1, 2. This is one plane of symmetry, one rectangular plane of symmetry. that is cutting like this. Okay, then the second one, the two opposite faces are these two, isn't it? So we can cut this cubic crystal system along this plane. Okay, so this is the second rectangular plane of symmetry. Then the third one, the two opposite faces, these two faces. So we can cut this cube along this plane. Okay, so you have to count the number of faces, and just the half of this number of faces will give the rectangular planes of symmetry. So here the rectangular planes of symmetry will be equal to 3. That is, it will be cutting the opposite faces. So total 6 faces are there, just the half. So 3 rectangular planes of symmetry. Then the next comes the diagonal planes of symmetry. Okay, the second plane of symmetry, that is the diagonal plane of symmetry. Diagonal plane of symmetry. So for that I will be drawing a cube. Diagonal plane of symmetry. So diagonal means just you mark the diagonals. This point. Okay, these are the corners. So here. Okay. So this is the diagonal plane of symmetry. That is, we are diagonally cutting that particular cubic system. Okay. So this is the diagonal plane of symmetry. That is, if we are cutting this cube like this. Okay. That is like this. This is the diagonal plane of symmetry, cutting this cube like this one. Okay. So see, diagonal means it will be touching the opposite edges, isn't it? Opposite edges. See, this is the one edge and this is another edge, isn't it? So it will be touching the opposite edges. So how many edges are there for a cube? This cube has got number of edges will be equal to 12. Number of edges will be equal to 12. So cutting the 12 edges means how many pairs will be there? 6 pairs will be there, isn't it? 6 pairs. That means 6 diagonal planes of symmetry will be there for this particular cube. Okay. So you have to count the number of edges. So half of that. So this will be one plane. So while telling the plane, this number will be coming to half. Okay. So number of edges 12. So total 6 planes of symmetry will be there, or 6 diagonal planes of symmetry will be there for this cubic crystal system. So in total we can say that the number of planes of symmetry for a cubic system, how much will be equal to, it has got 3 rectangular planes of symmetry plus 6 diagonal planes of symmetry, isn't it? So in total 9 planes of symmetry will be there for a cubic crystal system. Okay, 9 planes of symmetry for a cubic crystal system. Then the next one, you have to go through the axis of symmetry for a cubic crystal system. The second element of symmetry, that is the axis of symmetry. Here it is you have to write in the plural form, axis. Okay, axis of symmetry for a cubic crystal system. See here, how many faces are there for a cubic crystal system? Number of faces means it has got 6 faces, isn't it? So it will be having a fourfold symmetry. Fourfold symmetry means, see, this is the center of the crystal, or this is the axis of symmetry of this particular crystal. This is the axis of symmetry for this particular crystal. So if I am rotating this crystal along around 360 degree, what happens is that, see, all these sides are same. Consider all these sides are the same. That is orange, then green, then red, then blue. Okay, all these colors or all these faces are the same. See, suppose I am rotating it along 360 degree. So I had got a similar appearance here, orange, then again similar appearance green, then again similar appearance red, then again similar appearance blue. Okay, so while rotating through this particular axis of symmetry, I had got the similar appearance. How many times? 4 times I had got a similar appearance. Okay, so 4 times similar appearance we had already seen. That means it will be having a fourfold symmetry. Okay, 4 times similar appearance while rotating along 360 degree. That means it will be having a fourfold symmetry. Okay, fourfold symmetry, or we can call it as a tetrad. Okay, fourfold symmetry, tetrad. So here it is having 6 faces, isn't it? 6 faces means the fourfold symmetry, it will be equal to 3. Okay, since it is having 6 faces, the fourfold symmetry will be equal to 3. That means it will be appearing, similar appearance will be occurring how many times? 3 times. Okay. Sorry, similar appearance will be occurring 4 times, isn't it? So similarly, total, so this is one particular axis of symmetry, isn't it? Along these 2 faces, it will be passing this particular axis of symmetry will be passing through this 2 faces, that is one white and yellow, isn't it? So similarly, how many faces are there? Total 6 faces are there. So the this blue, then again the opposite side, opposite face, that is green, isn't it? So here also one more axis of symmetry is there, isn't it? Like through this point, through this line, one more axis is there, isn't it? Then again another 2 faces are there, that is the orange as well as the red. Here also one axis of symmetry or one line of symmetry will be passing. Okay, so thus it has got in total 3 fourfold symmetry. Okay, you have to write it as 3 fourfold symmetry are there, symmetry, axis of symmetry are there for this particular cubic crystal system. Then comes the number of corners. See, for a cubic crystal system, how many corners are there? See how many corners are there. See, 1, 2, 3, 4, then 5, 6, 7, 8, isn't it? So 8 corners are there, isn't it? Here it has got threefold axis of symmetry. See, threefold axis means while rotating through this this particular axis, what happens? The cube will be having similar appearance thrice. So that is called as a threefold symmetry or a triad, isn't it? Threefold symmetry or a triad. See how this axis of symmetry coming is that it will be like this. See, that means we are rotating that particular crystal along this particular axis, that is, see here, this is one edge, isn't it? So here so this is one corner, and this is the opposite corner, isn't it? Okay, these 2 are the opposite corners of this cubic crystal system. And also see, if we are passing rotating this crystal along these axes, see here we are rotating, it will be having through this axis of symmetry, that is along the 2 opposite corners, we will be having similar appearance thrice. Okay, if we are rotating this cube around a 360 degree angle, what happens? We will be having similar appearance thrice, and it is called as a triad. And also for a cubic system, see, it has got 8 corners, isn't it? For a cubic system, it has got 8 corners. So the threefold axis, number of threefold axis, it will be 4. Okay, so the rotation, it will be like this, just through the opposite corners, it will be like this. So like this, 1, isn't it? Similar appearance we will be having 3 times. So this is one opposite corner, then again this is the second opposite corner, these 2 are the second opposite corner, then the next one, the third one, and the next one, this is the 4th one. Okay, so these are the what is it, 3 fourfold symmetries or the triads for this cubic system. So for triads, for counting the triads, you have to count the number of corners and then write it as the half of that particular number of corners, and it will be equal to 4. Then coming to the dyad or the twofold symmetry. Twofold symmetry. For twofold means if we are rotating through 360, it will be appearing twice. So it is called as a dyad. Dyad. And also here you have to count the number of edges. So for a cubic crystal system, it will be having 12 edges. So 12 edges means the number of twofold symmetries or number of dyads will be equal to just the half of this edges. That is 6 dyads will be there. So the rotation, it will be through the edges. Okay. So if the line, it will be passing, this is one edge. So just the opposite of this edge, it will be this one. Okay. So if the line, it is passing through these two edges, we can have a twofold symmetry. Sorry. This is one edge and just the opposite of this one. This is the opposite edge. So if we are rotating like this, okay. I can't rotate through this camera. Okay. So just rotate, take a cube and just rotate these opposite edges. So likewise, you have got 12 edges. So the lines of symmetry or the axis of symmetry will be 6. So the here you have got how many axis of symmetries? Fourfold symmetry, it is 3. Then threefold symmetry, it is 4. Then twofold symmetry, it is 6. So the total number of axis of symmetry. Total number of axis of symmetry for a cubic crystal system. It will be equal to fourfold 3. Then threefold 4. Then twofold 6. So how much? 6 plus 4, 10, 10 plus 3, 30. Okay. So total axis of symmetry will be 30. Then the third element of symmetry, that is the center of symmetry. Center of symmetry. And see here, the center of symmetry for this particular cubic system, it will be only one. It will be inside this crystal system, that is at the center. That is like this. So here, this is the center of this crystal system. So only one center of symmetry for this cubic crystal system. So in total, we can write the elements of symmetry for a cubic crystal system. For a cubic crystal system, the elements of symmetry, it will be equal to how much? See how many planes of symmetry are there? That is, it will be having 3 rectangular planes of symmetry and 6 diagonal planes of symmetry. That means the total planes of symmetry will be equal to 9, isn't it? So 9 planes of symmetry. 9 planes of symmetry plus then how many axes of symmetry? Fourfold 3. Fourfold 3. Then threefold 4. Then twofold 6. So total 13 axes of symmetry, isn't it? So 13 axes of symmetry plus 1 center of symmetry. Okay. 1 center of symmetry. So in total, how much? 13 plus 9 plus 1. That is 13 plus 10. That is 23 symmetry elements are there for a cubic crystal system. 23 elements are there for a cubic crystal system. So this much you have to study for this session. In our next session, we have to go through the point groups. I hope you are clear with this symmetry elements. You just go through it, and if any doubt arises, you can ask me. Okay, thank you.